So we continue with our class on statistical mechanics. If you remember, in the last class we discussed about a case where four coins were tossed, and what we got was it produced 5 macrostates and 16 microstates. Hope you remember that. The microstates were what? 4H, 3H1T, 2H2T, 1H3T, and 4T. So these were the macrostates, and corresponding to that there were different possibilities in which this kind of a state can be achieved. This was 3H1T, which means 3 heads and 1 tail, was 4, and this was 6, this was 4, and this was 1. Hope you remember what we did in the last class, right? So we continue with that, which means that in order to build different macrostates, there are different ways. For example, the 2H2T, 2 heads, 2 tail, can be built up in 6 different ways. And each of these different ways, we call them as microstates. Coming to a thermodynamic system, we define the systems as we classify the systems into different macrostates, and these macrostates can be classified into can be considered to be built up of different microstates. So basically, here in thermodynamics, the macrostate defines a system in terms of macroscopic parameters N, V, and E. So in thermodynamics here, in thermodynamic system, the macrostate defines a system in terms of the macroscopic parameters N, V, and E. Now this macrostate can be achieved in lots of different manners, right? For example, you have different energy states like this, right? E1, E2, E3. So, and if you have got n number of particles in total, this n number of particles can be distributed in different manners, right? And again, if the particles are distinguishable, each of these organization will lead into different microstates. So in that situation, I can tell that this energy can be distributed among n particles in different ways. right? And each of this manner or way can be called as a microstate. As a microstate. So there is a more general way in which we can talk about this. We can always talk about these things in terms of its quantum mechanical counterparts, right? So in general, the various microstates can be identified with independent solutions of psi of R1, R2, etc. up to Rn of the Schrodinger equation. Right? Only thing which makes them together is that all of them are having their eigenvalue, say E, corresponding to an energy eigenvalue E of the concerned Hamiltonian. So now you can ask me, so whether this so-called macro state will go on changing forever. The answer is that it won't happen. Basically the macro state, the macro state will be stable if the system is in equilibrium, or the macro state won't change if a system is in equilibrium. Now you can ask me, so sir, in this example where we have having 4 coins tossed, right? So which is the equilibrium state? The answer is that here the 2H2T represents the equilibrium state. Right. Why? Because a macro state will have its equilibrium state corresponding to a system will have its equilibrium macro state corresponding to that situation which is having the highest number of possibilities or highest number of microstates. So here 2H2T is the one having the highest number of microstates, and therefore I can tell that this will be the equilibrium state. Okay. Okay, so we continue in the next video.